welcome. In this session, we'll explore what it means for a direction to be a descent direction of a function that has a vector argument. The basic idea is that if we're given a current estimate of a minimizer and we go to a new one, so we take one iteration, what we do is we want this to be an improvement. So we want the level of the function at the k+1 iteration to be an improvement on the level of the kth iteration. So what we'll do is we'll locally define a descent direction. So this is a direction in which the function's level will decrease, a descent direction d at. Now, for this session, we'll put a 0 here to indicate that this isn't true for every argument. What we'll do is we'll hold a specific value of the argument and we'll say that at that specific value of the argument, what we want is we want this to be an improvement. And if it's an improvement, that means that the directional derivative is heading downward. So what we'll say is that the derivative in direction d of the function at that definite point has to be strictly less than 0. So intuitively appealing, this was part of our motivation for this lecture. Intuitively is we want the steepest descent. That is, we want locally at some point, we want the local optimum, the local best thing that we can do. So what we'll do is we'll use a unit vector, and later in this session we'll remove that requirement, but we'll use a unit vector d, and what we mean is that the length of d is 1. So now we can define what we mean by steepest descent. So this will be, we'll say d is the result of a minimization process. That is, we want to find the argument which is the unit direction that has the smallest directional derivative. So that would be looking over all of the vectors in the vector space that have unit length. We want that vector v such that the derivative in direction v of the function at this definite point is as small as possible. So let's recall from previous lectures, that we can write this directional derivative using the gradient. So we can say that the derivative in direction v of a function at a point is the gradient 1 form of the function at that point times the direction. And here we're supposing that v is unit length, so it's non-zero, so this works. So now we can substitute. And when we substitute, what we see is we just substitute into this, we'll substitute this gradient expression. So that is that d is now the argmin over all unit vectors in the vector space of the gradient 1 form of the function at the point times the direction. And we could write that further as we can say that that is over Rn of the length of V is 1, we can say here we have a one form times a vector, and it may help us to think if we say, well, a one form times a vector is the same thing as a transpose one form dot a vector. So we can say that's the gradient one form transposed dot V. And now we can use linear algebra. So this is a fact, meaning it's a proof that you can find in other sources. Let's think of this. So V is a unit vector. So what direction has the maximum, let's say, with V? So if let's suppose that this is a unit vector, and what we'll do is actually, let's make that a unit vector. Let's try that. So let's say that that is, sorry, not there. Let's say that this is what we have. This is a unit vector, V is a unit vector, so the dot product of two unit vectors is at most 1, and the dot product of two unit vectors is at minimum -1. So where would it be 1? Well, it would be 1 if that exactly equaled V. Where would it be -1? It would be -1 at exactly the opposite. So we know that this argmin has a simple solution, and that is the argmin of this is so if D is a unit vector, so that solves from linear algebra as that D is, so if V equals that, it's 1, and if V equals minus that, it's -1, and the dot product of two unit vectors can never be outside that domain of -1 to 1. So we then know that it is minus the gradient one form of F evaluated at the point that we're looking at, made into a unit one form by dividing by its magnitude, transpose. And what we'll often do in our descent is that we'll now say, now we'll allow D to have a general, let's put that in quotes, a general magnitude. That is, now let's suppose that as part of our iteration, what we want to do is we want to include the magnitude of the gradient as well as that unit direction. So we will use our direction at step K. So now let's be specific here. At step K is minus the gradient of F evaluated at iteration K, and we transpose that. And now our iteration from, you can think of this as we're now going to incorporate not just the previous session, but we're going to go back several lectures back into scalar land, is that our extension from scalar land is that the k+1 iteration of our estimate of the minimizer is our k iteration, and now we say plus s times d, and that would be minus sk times the gradient one form of f evaluated at k transposed. And this is referred to as the steepest descent, and other texts may call it gradient descent, but really it's not just the gradient. What they're doing is they're really trying to aim at going in the steepest descent. Now let's go through an algorithm for steepest descent with a fixed step size. We'll require the user to provide us with a maximum iteration number and with a limit on the gradient magnitude that they'll accept. We'll initialize our estimate to their first estimate. We'll note what the current function is. We'll find the gradient, and we'll set the descent direction to be the negative transpose of that gradient one form. We'll start off at iteration 0. While we haven't converged, we'll use a fixed step size update on the current estimate of the minimizer. We'll recompute the descent direction. We'll reset the current function value. We'll update our iteration variable, and we're done. So this is a very straightforward and simple implementation.